You see, there you are. You should be able now. Luis, I still see you're raising your hand. I just let you to Martin. Let me see. There you are, Martin and Brian. Here you are. Guys, please check and let me know really quick because I want to go ahead and start the lecture. Brian, you should be able now, and Martin, I just allow you to record, all right?
Yes, Professor.
Okay, good. So it seems that we are all good. Once I share my screen, I don't want to go back to make sure you let me know right now. Let me share my screen with you guys. And I believe we haven't finished the first slideshow yet. Let us see when we should pick up. All right. Last time we talked about dimensions and units, and also we talked about British gravitational system, system, and English engineering system. And we talked about some unit for heat. We talked about system and control volume, and also control surface, which is the border of control volume. We talk about closed and open system, and we talk about extensive and intensive property. I think we should pick it up from here. Let's define density. I'm sure you all know what density is. We show the density with a Greek letter rho, and that is physically, it means mass per unit of volume. And if you divide mass of a system by the volume, that gives you density. And inside system, the unit for density is kilogram per meter cubic, right? In British gravitational system, when the unit for mass is a slug, that's going to be a slug per feet cubic. And in English engineering system, that is pound mass per feet cubic. Now we want to talk about specific gravity. SG stands for specific gravity. That is the density of the fluid divided by density of water at a specific temperature, which is 4 degrees centigrade, and that is 1,000 kilogram per meter cubic, or 1 gram per centimeter cubic. It's also equal to 1 kilogram per liter, because 1 meter cubic is equal to 1,000 liter. In a British gravitational system, it is 1.94 slug per feet cubic. If under notes, I wrote that if a specific gravity of a fluid or a specific gravity of anything is less than 1, it means it floats on water. For example, oil, specific gravity for oil is less than 1, it's 0.7, 0.8, and that floats on water. So a specific gravity, Hg, the density of fluid divided by density of water at specific temperature, which is 4 degrees centigrade, and density of water at 4 degrees centigrade is 1,000 kilogram per meter cubic, or 1 gram per centimeter cubic, or 1 kilogram per liter. Keep that in mind. 1,000 liter is equal to 1 meter cubic. What else? You see specific gravity a lot in fluid and in thermofluid, and also in thermodynamics. So it's important to know the definition. As I told you, chapter 1, we just jump from one subject to another, and some definition that we're going to use in following chapters. We are done with the first slideshow from chapter 1. It seems that we just had a couple of slides left. Now we can go ahead and start session 2 from chapter 1. Here we are, session 2 from chapter 1. I don't know why it takes so long. All right. So it's not audio recorded, though. We want to talk about state and equilibrium. And see, there are different types of equilibrium. You hear this term like thermal equilibrium, and that's where the temperature throughout the system, throughout the entire system, is the same. Then we say that it's reached thermal equilibrium because temperature is uniformly distributed, the same throughout the whole system. There is, other term which the word equilibrium, like chemical equilibrium, means there is no more chemical reaction in the system. Or phase equilibrium. Sometimes there are different phases, more than one phase, like two more phases. For example, we may have mixture of liquid and vapor water. And when we use this term phase equilibrium, it means that there is no more changing phases. Mass of each phase is remains constant. It is at equilibrium phase equilibrium. Then you hear the word state a lot in this course. There are some properties that they describe a system. For example, temperature or pressure or density. There are some value of some properties that they have point value. And when you know the state of the system, when the system, the state is fixed, the value of those properties are fixed too. For example, you say, okay, the system is at a state 1. Here is the temperature, T1. Here is the pressure, P1. The value of those properties basically describe the of the stuff. By the way, in order to, fix the state, in order to describe the state, we don't have to specify all the properties, value of some key properties, they are sufficient to describe the state, for example, pressure and temperature, And there is also process. You hear the word process. The state, the system basically goes from one state, for example, state 1, to another state, let's say state 2, through a process. So the system undergoes a process, and that takes the system from one state to another, from a state 1 to a state 2, from a state 1 with P1, T1, and value of all of those properties to a state 2 with P2, T2, and so on. A process can be isothermal, meaning that during this process, going from a state 1 to a state 2, the temperature remains constant. That makes the process isothermal. The process can also be isobaric, meaning the pressure during this process is constant. So if the pressure is constant, we refer to that process as isobaric. And also the volume of the system can remain constant during this process. Volume being constant means the process is isometric. So the isothermal means the temperature remains constant. You are going to hear these terms, and we are going to have different cases under different conditions for different processes. Also, another thing you need to know about is cycle. If the initial and final state are the same, look at this figure, please. We have some type of diagram. For example, it can be PV diagram or PV diagram, but T, I mean temperature, P means pressure, V, specific volume or nu, let's say. So if the system goes from a state 1 with value of P1, V1, Nu1, H1, U1, these are value of properties, pressure, temperature, enthalpy, internal energy, specific volume, to state 2 with value of those properties being equal to P2, T2, Nu2, U2, H2 under this process, let's say process A. And then it goes back from a state 2 to a state 1 through process B. We say that the system undergoes a cycle because, as you see, the initial and the final state, they are the same. So the system goes back to its initial state during a cycle. That's the meaning of a cycle. It consists of processes, and the initial and final state are the same.
Professor?
Yes.
So if in that cycle, if we return to the initial state, is that what you call the steady state process, or is that something different?
No. A steady state is different. I'm gonna explain the steady state in a second, but that was just the definition for cycle. I'm gonna, explain steady state. See, when you say we are under steady state condition, it means that nothing changes with time at a fixed point. For example, if there is a fellow field and you are sitting at a specific point, let's say point A, with a given coordinates, XA, YA, ZA in Cartesian coordinate. You are sitting at this given point, imagine, and you have a piece of paper and you're writing down the value of properties in this given point at this fixed point in the fellow field. You have the very first column as time, T1, T2, T3, T4, T5. And the second column, let's say, it shows temperature. The third column shows pressure. Temperature at A, pressure at A, the very same point that you are sitting. And you are writing down the value of all of those properties as a function of time, and you see no changes. You see that temperature is fixed at this given point, pressure is fixed at this given point. So you would say steady state. So nothing changes at a given point with time. Nothing changes with time at a given point. By nothing, you mean the value of all of those properties remains constant. Velocity of the fluid particles passing through that fixed point, the pressure at that fixed point, the temperature at that fixed point. Imagine a cup of tea. It's not the case of steady state because at a given point, the temperature continuously changes with time, so it's a steady state. There is also another way to explain a steady state. For a device, when we say we are under a steady state condition, or this is a steady state device. So we are under a steady state condition. If, for example, if there is a control volume, there is this control volume. We define the control volume. It can be the boundary of, the control volume can be a section of pipe. It can be a duct. It can be throttling valve. It can be a part of heat exchanger. It can be anything. And it can be pump. It can be turbine. And when you refer to this word steady state, it means nothing changes inside this device with time. For example, mass of fluid inside this device doesn't increase or decrease with time. Momentum of the particles Although at different time, there are different system inside, there are different fluid inside because the system is open. For example, imagine a section of pipe, the system is open, there is inlet, there is outlet, flow, there is inflow, there is outflow. And if you look at the system at different time, there are different particles inside and they have different velocity, but the momentum, whatever happens inside the system, the momentum doesn't change. Momentum of the system doesn't change. It doesn't increase. It doesn't decrease with time. The mass inside this device doesn't increase, doesn't decrease with time. The energy, although different, fluid is inside, and this particle at different internal energy, they have different velocity, and as a result, different kinetic energy, and they have, but whatever happens, somehow energy inside this device doesn't increase or doesn't decrease. If nothing changes inside this device or inside this control volume with time, then you say it's steady state. Or another way to define it, nothing changes with time at a given point. Of course, things changes with time, but at a fixed point, when you are looking at things doesn't change. That's the meaning of steady. So here in this slide, I explain what I just explained to you. A steady state process, mass, energy, volume, everything remains constant inside the control volume. It doesn't increase, it doesn't decrease. Devices like turbine, pump, fan, condenser, heat exchanger, we're going to learn about those later, starting from chapter 2. These devices, they work in periodic manner. I have a question for you, and I give you 1 or 2 minutes just to think about that. Then I'm going to explain myself. Or if there is any volunteer, you can explain it too. See, look at these devices. Think of these devices. Think about these devices. For example, turbine, pump, fan. We all know that they work cyclically, periodically. And now, if, for example, consider a fan and look at point A with coordinate XA, YA, ZA. At this given point, we know that velocity changes with time. It doesn't remain the same. Temperature changes with time. It doesn't remain the same. Pressure can change with time, changes with time, and it doesn't remain the same. Can we consider these devices, this process, as steady state? Yes or no? I don't want any answer now. I give you 2 minutes just to think about that. And if there is any volunteer, you can answer. Otherwise, I am gonna to explain this. Okay, so your time starts. 2 minutes. Is there anyone who wants to answer my question about what can we say about these devices? Because we know that they work periodically, and can we consider them as steady flow devices? Yes or no? Anyone?
Yes, Professor.
Yes or no? Can you talk a little bit louder, please?
I think that would be yes.
Yes, your answer is correct.
So
And
because as you explained, nothing changes. So I think that we can call them steady state.
see, for example, if you consider fan at a specific point, let's say point A, we do know that with time, temperature at that given point changes, pressure changes, velocity changes. But here is the thing, it changes periodically. It changes periodically. That's why we say there are steady flow process or steady flow devices, but on time average basis, or they are, steady in mean. So when you hear the word steady mean, or steady on average, or average basis, then you know you are dealing with some sort of devices which work periodically, you know. So we do consider, you are correct, we do consider them as steady flow devices and steady process, but just you add this word on average basis or in mean. But if it's just steady, it means that nothing changes with time at a fixed point. In this case, it does changes, but it changes periodically, you know. So it just goes back to, it just works on a cycle. All right, thank you. Now we want to talk about thermal equilibrium. See, there are two different bodies with two different temperature, and one of those body has higher temperature, the other one has lower temperature. And we do know that automatically nature, the difference in temperature is the driving force, and heat is being transferred from the body with higher temperature to a body with lower temperature, right? So that heat transfer continues, and the temperature of the body, which has the higher one, drops and drops, decreases and decreases, and the other one increases and increases. And at some point, they reach very same temperature, and the heat transfer stops. And we say that they reach thermal equilibrium. That is the meaning of thermal equilibrium, right? Now we want to talk about Zeroth law of thermodynamics. It's very simple. It says that if there are two bodies that there are at thermal equilibrium with the third one, they are at thermal equilibrium with themselves, right? Because if there is, imagine there is body one and body three, and there is body two. And body one and two, they're at thermal equilibrium, meaning that there will be no heat transfer between them because they have the same temperature. And body three and body two are at thermal equilibrium because they have the same temperature and there is no heat transfer between them. So body one and body three, they will be at equilibrium themselves, even if they are not in contact. They have the same temperature because both are at thermal equilibrium with the third body, right? And now we want to talk about, the absolute temperature, thermodynamic temperature, Kelvin and Rankine, and relation of those with centigrade and Fahrenheit. We all know that we can convert, the Celsius or centigrade to absolute temperature in SI system, which is Kelvin or thermodynamic temperature, by adding 273, to be exact, 273.15. So temperature in terms of centigrade plus 273 converts it to Kelvin. And for Fahrenheit, which is in British gravitational system and English engineering system, if you add 460 to Fahrenheit, that converts it to Rankine, which is absolute temperature in English system or British system. So that's a conversion you need to know because it's a formula. You have to use the temperature in terms of absolute, like ideal gas law. You cannot use Fahrenheit or centigrade, right? And there is relation between Fahrenheit and centigrade. For example, me, myself, I always have, the Fahrenheit doesn't make sense to me when you say, okay, here is the temperature in Fahrenheit. In my mind, I have to convert it to centigrade for me to make sense, okay, how cold or how hot it is, and here's the conversion between centigrade and Fahrenheit. You multiply centigrade by 1.8 and then add 32. And here's the Fahrenheit. So if they give you a temperature in terms of centigrade, multiply by 1.8 and add 32. And here's the Fahrenheit. If they get the temperature in terms of Fahrenheit, subtract the 32 and they divide it by 1.8. And that is centigrade, right? So here is the conversion formula for conversion back and forth between centigrade or Fahrenheit, because sometimes you have the temperature in terms of Fahrenheit and you need to convert it to centigrade and vice versa. What is the relation between Rankine and Kelvin or centigrade or Fahrenheit and centigrade? See, Rankine, temperature in terms of Rankine, it's 1.8 temperature in terms of Kelvin. So here is the scale. 1 degree Kelvin is the same as 1 degree centigrade. The same. If they tell you what is the difference between two temperatures, T1 and T2, doesn't matter if you convert it to Kelvin both or just deal with centigrade. Doesn't matter. Because if T1 and T2 both expressed in centigrade, you can, subtract them, and here is delta T, right? And if you convert both to Kelvin, add 272 to each, 272 cancel out when you subtract. 1 degree of Kelvin on a scale is the same as 1 degree of centigrade. The same. In other words, 1 degree of Fahrenheit is the same as 1 degree of Rankine. But when you compare centigrade or Kelvin, this is put them in one package. And Rankine and Fahrenheit put them in package because its distance is equal for Fahrenheit and Rankine. This distance is equal for Kelvin and centigrade. But if you compare this package with this package, Rankine or Fahrenheit on a scale is larger. It's 1.8 times larger. So you have to multiply Kelvin or centigrade by 1.8 to get it in Rankine, right? So here is the, delta means the difference. Difference in temperature. So how do you read it? Difference in temperature in Kelvin is the same as difference in temperature in centigrade. I just explained. T1 and T2 both are centigrade. Difference between these two, for example, 40 degrees centigrade and 30 degrees centigrade. What is the difference in temperature? 10. Difference in temperature in centigrade. What is the difference in Kelvin? Okay, you add 273 to, one of them is 10, one of them is 30. You add 272 to this one, 272 to the other one. Cancel out. So difference of temperature in Kelvin is the same as difference in temperature in centigrade. The same with Rankine and Fahrenheit, because in order to convert Fahrenheit to Rankine, just give me a sec, you have to add 460. So it doesn't matter if somebody tells you, okay, T1 is 40 degrees Fahrenheit, T2 is 60 degrees Fahrenheit. What's the difference? 20. And if you convert both to Rankine by adding 460, still the difference in temperature in Rankine would be the same. Keep that in mind. On a scale 1 degree Rankine, 1 degree Fahrenheit is equal on a scale. 1 degree Kelvin and 1 degree centigrade is the same. But when you compare difference in temperature in Fahrenheit and difference in temperature in centigrade, difference in temperature in Fahrenheit is 1.8 difference in temperature in centigrade. The same with Rankine and Kelvin. Difference in temperature in Rankine is 1.8 times larger than difference in temperature in Kelvin. I'm taking questions. Is there any question?
Professor, where do we use the units? Because honestly, I've heard everything else but that.
What was that? I couldn't hear you right.
Where do we use the Rankine? Is it going to be in the British scaling system and SI?
Rankine, yes. Rankine is in exactly British and English system, but Kelvin and centigrade are for SI system exactly. Yeah.
And Professor, that 1.8, we learned that it was 9, as in like 9/5. That's the same, right? The same formula.
What's that? 1.8?
Yeah, the 1 point. Yeah.
See, if you convert Fahrenheit and centigrade, yes. See, it comes from here, right there. 1.8.
Thank you,
Yeah.
Professor.
Of course. Any other question, guys? No question. Now we can go to the next one. See, I want to show it to you on this scale. That makes better sense. Here is SI system. We have centigrade, we have Kelvin. Here is a British system or British gravitational PG. British system or EE system, which is this stands for English engineering system. Fahrenheit and Rankine. So let's first work on SI system. As you see, here is absolute zero. We have Kelvin here on right side and centigrade on the left side. So here is absolute zero, right? What is absolute zero in terms of centigrade? We know Kelvin is centigrade plus 273. We just learned about the conversion between centigrade and Kelvin. Centigrade plus 273 gives us Kelvin. So if it's 0 Kelvin, put 0 here. What is the centigrade? Minus 273. The 0 or absolute 0, which is in Kelvin, 0 Kelvin or absolute 0, it's equal to minus 273 centigrade. What does that mean when we are at, here is the 0 centigrade. What is the conversion? Okay, put 0 here for centigrade, and that is equal to 273 Kelvin, right? So here is relationship between Kelvin and centigrade according to this formula that we learned. By the way, 0 Kelvin with absolute 0. We cannot go lower than that. And here is Fahrenheit and Rankine. Left side Fahrenheit, right side Rankine, right? By the way, on a scale, 1 degree centigrade and 1 degree Kelvin have the same size. Fahrenheit and Rankine. Okay, we are at 0 Rankine. What does that mean? What is it in terms of Fahrenheit? We know that Fahrenheit plus 460 gives us Rankine. To be exact, it is not 460, it is 459.67, but we round it up to 460. So Fahrenheit plus 460 gives us Rankine. So when it's 0 Rankine, which is absolute 0, put it 0 here. Then Fahrenheit would be what? Minus 460, right? So 0 Rankine, absolute 0 means we are at minus 460 Fahrenheit. And here is 0 Fahrenheit. 0 Fahrenheit, put Fahrenheit at 0, is equal to 460 degrees in terms of Rankine, right? Just use this formula, very easy. Now we want to compare these two. What does that mean? 0 centigrade to what? Okay, we know Fahrenheit. We know the conversion between Fahrenheit and centigrade. Fahrenheit is 1.8 centigrade per 32. We're at 0 centigrade. Put centigrade 0. That is equal to 32 Fahrenheit. Here we are. 0 centigrade, 32 Fahrenheit. 0 centigrade here means 273 Kelvin, right? 0 centigrade is 273 Kelvin. And it is equal to 491.69 or 492 ranking. So because 0 centigrade according to this is 32 Fahrenheit, and 32 Fahrenheit according to this, you should add 460. And here we are. So you can convert between these two. By the way, 1 degree on a scale, 1 degree Fahrenheit is the same size as ranking. But when you compare these two, Fahrenheit and ranking are 1.8 times larger than the difference in temperature in terms of centigrade or Kelvin. Now I'm taking questions if there is any. Is there any question, guys, before I go to the definition for pressure? As I said, chapter 1, it's just different subjects. We become more focused as we get to chapter 2. Actually, we are going to talk about the first law and then see the application of first law. Is there any question so far? Oh,
I have a quick question. So everything we're
yes,
seeing,
is your name?
everything we're seeing in chapter 1, we're gonna go more into depth in later chapters. Is that what?
Yes, exactly. Some of them, they're just definition, but yet we are going to talk about first law in really details, and we are going to, see the application. So yeah, chapter 1 is just like an introduction, some of these terms we are going to use later on, definition we are going to use later on, but yes, everything no worries, I'm going to explain everything in detail, really detail. All right, step by step. We want to talk about pressure now. Look, when you hear the word pressure is normal compressive force per unit of area. See, in other courses, you may hear the word stress, like fluid, like, deformable bodies, strength of material. So when you hear the word stress means force per unit of area. Stress means force per unit of area. It can be normal, which is normal force per unit of area. And normal force can be in form of compression or tension. Normal is perpendicular. Force is perpendicular to the area. So it can be, so stress is force per unit of area. Normal, we have normal stress, we have shear stress. Normal stress is normal force per unit of area. It can be grouped into, compression or tension. It can be in form of, tensile stress, or if it's compressive, it's compressive, right? And it can also be shear stress. Again, stress force per unit of area. If it's shear stress, shear is like friction. That is the tangent force per unit of area, tangent force. So we have normal force, we have tangent force. Normal force per unit of area gives us normal stress. Tangent force per unit of area gives us shear stress, shear and normal stress. And now we talk about pressure. Pressure means normal compressive force per unit of area. As you see in the figure, the force is normal, which is perpendicular to the area, is compressive. So it's not tensile, it's not in form of tension. So normal compressive force per unit of area, that's the pressure. So P is F divided by A. In SI system, the unit for pressure would be Newton per meter square, which we call Pascal, right? And we also have kilopascal, which is 10 to the power of 3 or 1000 Pascal. We also have megapascal, which is 10 to the power of 6 Pascal. Now I have a question for you. Is pressure scalar or vector? I give you 1 minute just to think about that. Then you can answer. 1 minute. Okay, anyone can explain if pressure is scalar or it's a vector?
Professor, I believe it should be a vector. That's force is a vector.
Okay, what do you think, Martin?
I believe pressure is a vector because it requires both a direction and a magnitude.
Okay, see, actually it's a scalar. You know why? Because we already know the direction. We know that it's compressive, right? And it is normal. So when we refer to pressure, actually, we just mean F divided by A. So it's just the magnitude, you know, we already know the direction. It's compressive and it's normal. So pressure is considered a scalar. So thank you guys. I like when you participate. So that's the whole point here. So the other unit for, pressure specifically for atmosphere, we use the term bar. These are, usually used for atmosphere. They are being used in Europe. Bar and atmosphere, ATM for atmosphere and bar. 1 bar is 10 to the power of 5 Pascal, which is 100,000 Pascal, or 100 kilopascal, which is 0.1 megapascal. So you don't need this part. 1 bar is 100,000 Pascal, or 10 to the power of 5. 1 atmosphere, there is also 1 atmosphere, which is a bit larger than, bar. That is 101, 101, I mean, 101,000, 325 Pascal or Newton per meter square, because Pascal Newton per meter square, right? So that's that, atmosphere and bar. And if you want to compare atmosphere with bar, 1 atmosphere is 1.01325 bar. 1 atmosphere is 101.325 kilopascal, 101.325. I'm going to skip this part because we are not going to use it. So it's useless. It's not useless. I, used to explain, but we never use it in this course, so I just skip. We also want to talk about Psi and Psf, which are unit for pressure in English system, and as well as British system, because in both English and British, the unit for force is pound force, which we casually say pound, and the unit for length is feet. So for the area would be a square feet or a square inch, right? So when we say PSI, what we mean is pound per square inch. So pound per square inch. We can rewrite it as pound per square inch. Both are the same, pound or pound force are the same. And when we use PSF, that's pound per square feet. Pound per square feet or pound force per square feet, right? And if you want to compare 1 atmosphere is 14.696 psi. You can round it up to 14.7. By the way, the reason we use the word atmosphere for this unit, because it's a standard condition. The pressure of atmosphere at the sea level is 1 atmosphere, which is 14.7 psi. So that's the pressure of atmosphere at the sea level at a standard condition. Pressure of atmosphere at the sea level at the standard condition, 14.7 psi, which is equal to 1 atmosphere. That's what 1 atmosphere means. Pressure of atmosphere at sea level at the standard condition. So in terms of unit, 1 atmosphere is 14.7 psi. Now we want to talk about absolute or gauge pressure, because throughout the course, as well as fluids, you hear the word absolute pressure or gauge pressure. Absolute pressure is where you measure the pressure relative to what? Relative to perfect vacuum. Absolute zero. You cannot go lower than that in terms of pressure. So, for example, there is a fluid, and you measure the pressure of the fluid relative to perfect vacuum, relative to absolute pressure. So the absolute pressure is always positive because pressure of anything is above perfect vacuum, right? So absolute pressure is always positive. Then we also have gauge pressure. Look, if we know that pressure of atmosphere is at zero, atmosphere has some pressure, right? The local pressure of atmosphere comes from the weight of atmosphere from that point up to the end of the atmosphere. So pressure of atmosphere is not zero. Atmosphere, of course, has pressure, but sometimes you use it as a reference. You set it equal to zero because you wanted to use it as a reference. The same with elevation. Remember, for example, we know that the table you are sitting at, it has some elevation, but you can set it equal to zero and use it as a reference and measure the elevation of everything relative to that table. So we set the pressure of atmosphere equal to zero because we want to use it as our reference. And then we measure the pressure of everything relative to pressure of atmosphere. So if the pressure of the fluid is above the pressure of atmosphere, that's positive. If the pressure of fluid is below the pressure of atmosphere, then it is negative. So gauge pressure, it can be positive or it can be negative. It depends if pressure of fluid is above pressure of atmosphere or below the pressure of atmosphere. So gauge pressure, when you express the pressure of the fluid in gauge, that is basically the excess of the pressure of the fluid over the pressure of atmosphere. It can be positive or negative. According to geometry, just if you have a line that shows the perfect vacuum and then above that line, there is a pressure of atmosphere and the distance between these two is pressure of atmosphere, then if you consider a fluid with a pressure above the pressure of a local atmosphere, then the distance between pressure of atmosphere and pressure of the fluid, that is the gauge pressure of the fluid, and that distance plus the distance between the pressure of atmosphere and absolute pressure, that shows the absolute pressure. So the absolute pressure of the fluid is the gauge pressure of the fluid plus the pressure of atmosphere. So ABS for absolute pressure of the fluid is gauge pressure of the fluid plus pressure of atmosphere. I wish I had a figure for you that show it better, but I don't. But you can, draw it yourself and, have a line that shows absolute pressure or absolute zero, I mean. And then here is the pressure of atmosphere. This distance shows the pressure of atmosphere. And then there is another fluid. Let's say the pressure of the fluid is above the pressure of atmosphere. And this distance is absolute pressure of the fluid, which is a summation of these two distances. This part, the distance from pressure of the fluid to the pressure of atmosphere, is gauge pressure of the fluid, and then this distance, which shows the pressure of atmosphere. So pressure of atmosphere plus the gauge pressure of the fluid is the absolute pressure of the fluid. We have the formula right here. ABS shows absolute pressure of the fluid, gauge means gauge pressure of the fluid, and ATM means pressure, right? Now we want to talk about before that, let's take question. Is there a question, guys? Please ask me if you have any question. No question for me? Is everything clear? Let's put it this way. Is everything clear enough? I need the confirmation before I proceed.
I think it is.
So far, so good.
Okay, good. So far, so good. It's good. Thank you. Let's talk about variation of pressure. See, when you talk about pressure, we learned that pressure is compressive normal force per unit of area, right? So here is the area, right? And normal compressive force per unit of area. So F divided by A is the force is not normal. You have to resolve it into two components, tangent and normal, and just consider the normal part of the force and divided by the area. That's pressure, normal compressive force, right? That's the definition for pressure. So it's kind of like compressive stress, right? So we already know that direction is normal, it's compressive. So we treat it like a scalar because when you talk about pressure, you just think of the magnitude of that. So it's normal compressive force F divided by area, right? So we not only need the force, we also need the phase. So think about that. What do you mean? What do you mean when I tell you, here is the pressure at this given point in this fluid? At this point, like point A. Point A, that's some random point, arbitrary point in the fluid. It can be anywhere in the fluid, just some random arbitrary point. And I tell you, here is the value of pressure at this point. What do I mean? You need a surface to measure the pressure. What do I mean when I say, here is the pressure at point A in this fluid? I give you 2 minutes just to think about that. Then if there is any volunteer, you can explain. Otherwise, I am going to explain. All right. Anyone can explain what do we mean when we say here is the pressure at point A? Pressure is there's the flow field, and A is just some arbitrary random point in this flow field, and here's the pressure at point A. What do we mean by that?
The
Anyone?
weight, Professor, can we say it's the weight of everything above it?
What's that?
The weight of other molecules or whatever it is above that point?
You are right. Later on, we will see that when we want to calculate, that's the weight of column of fluid above that. But before that, we have to prove that pressure is independent of direction. We are looking at point A. See, here's the thing. A is some random point in the fluid, right? Some random point, arbitrary point. It can be anywhere. Consider a cubic that A is at the center of that cubic. Just a differential cubic, a small differential cubic. A is at the center of that cubic. Then consider pressure. There are 6 surfaces to that cubic: top, bottom, right, left, front, back. And consider the pressure from the rest of the fluid on top surface, on bottom surface, on the right surface, left surface, front surface, and back surface. Because we can define pressure on each surface, right? Which is compressive normal force on the top surface, or on the bottom from the rest of the fluid, on the front, on the back, on the right, on the left. There are pressure, right? And when the dimension of this differential cubic approaches to 0, becomes smaller, 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 and eventually it becomes a point. What point? Point A. Very same point A. So when you say pressure on top of that cubic, and eventually the dimension of the cubic goes to 0, and that cubic becomes a point. What point? Point A. Then pressure on at A, when you look at it from this direction, when you pass through a surface from A, this surface I'm talking about, this is the pressure at A. From the bottom, this is the pressure at A. From the front, it's perpendicular to the board. From the back, it's perpendicular to the board in the opposite direction. In the right, you consider this surface passing through A, right and left surface of the cubic, which is in this direction, right? Vertical. And pressure at A, when you pass through a page from point A, vertical, right and left, that is pressure at A, right? So you consider a cubic around point A such that A is at the center, and then there's pressure on the top, bottom, right, left, front, back of that cubic. Eventually, that cubic becomes a point, point A. And just imagine when you talk about pressure on the top surface, bottom surface, right, left, front, back. These are pressure at point A when you pass through different surfaces from A. If you pass through this surface from A, then this is the pressure at A from this direction. Pressure at A from this direction, pressure at A from this direction, pressure at A from this direction, pressure at A perpendicular to the board, right? When you pass through this surface, when you pass through the surface which is parallel to this slide. So pressure on the front and back at A. Now the next question is, now I have an understanding of what pressure means at a given point, right? You are looking at that point from different direction and pass through surface from that point, and then consider normal compressive force at that point on that surface. And that is the pressure at that point when you are looking at it from that specific direction. Now comes the next question. Does it matter from which direction we are looking at point A? Does it matter if you calculate the pressure at A when you pass through this surface and consider this pressure? Or you pass through this surface from A and normal compressive force, which is this force. A. Or you pass through this surface from A. Because in order to define the pressure, not only you need a point, you need a surface. So you pass through this surface from A, and normal compressive force at A on this surface becomes this, right? This direction, because this is the surface. So that's the direction for. So does it matter from which direction we are looking at A? Now comes the second question. Think about that. And then I'm going to explain. I'll just give you 1 minute to come up with something, and then I'm going to explain it myself. Just 1 minute. What do you think? I just like to know, what do you think? Does it matter? We look at point A, from which direction do you get different value for pressure?
No.
No.
No, you are correct. Because here is the thing. If there is no shear, doesn't matter. Pressure at any random point, at any point like point A, is independent of direction. Doesn't matter from which direction you're looking at it. Doesn't matter which surface passes through A. Pressure at A from this direction is the same as pressure at A from this direction. It's the same as pressure at A is the same direction. So if you just pass through, if you rotate this page, 360 degree, right? It just doesn't matter. Pressure is the same. If there is no shear stress, that is Pascal law. If there is no shear stress, we proved that in fluid mechanics, ME 360, I proved that for my student. If there is no shear, then we can say pressure at any given point in the fluid is independent of the direction. Okay, and you know why? We can prove that. I wanted to explain something, I just forgot. Okay, now the third question comes. When you can claim shear is zero? Okay, no motion, no friction. If you are talking about, for example, water in the tank, no motion, no friction. Even if water is viscous, even if water is viscous, and if there is motion, there will be friction within the water, between the layers of water. But because no motion, no friction, because motion creates resistance like friction. No motion, no friction, even if water is viscous. So if there is no motion, like you think of water in a pool, water in the tank, then you can claim shear is zero. No motion, no friction, no shear. Another case is fluid is inviscid. There's no viscosity. There's no shear, even if it's moving, like air, So in the case fluid is viscous, if there is no motion or friction like water in a pool, or sometimes viscosity of the fluid is negligible. There's no such a thing in real world to have a fluid with absolute zero viscosity. But sometimes viscosity is negligible, like for air. In those cases, there is no shear stress. There is no tough or shear stress. Shear is like friction. It's like tangent force divided by the area. It's like friction. So if there is no shear stress, then you can say pressure at any random point in the fluid is independent of direction. Pressure at A from this direction, if you pass through this surface, is the same as if you pass through this surface. The pressure is in this direction because it's compressive normal to the surface at this point. It's the same in all direction. There is no friction. And if that's the same now, the next question would be how I can calculate it. How I can calculate it. I'm gonna give you a minute just to think about how you can calculate. We can prove, but I just want for you guys to think about that. And now that I know pressure in the fluid at rest, when there is no friction, or for the fluid that by nature has no friction, is like air is independent of direction, how I can calculate that? Think about this. Oh, I'm gonna stay on this surface, this page, sorry. As your friend, one of your friend explained before, it comes from the weight of the fluid above that point. Weight of the fluid, think about that. I want to get you thinking. What time is it? Is it 6:45?
It's 6:44 right now.
Okay, I'm gonna stop at this point. We run out of time, right? It's 5, or we have time. It's 5:30 to 6:45. So I'm gonna stop at this point, and next time I'm gonna pick it up from here. All right. So think about that. How we can calculate pressure now that we know it's independent of direction when the fluid is stationary or when the viscosity in the fluid is negligible. So there will be overall when there is no friction, when there is no shear stress, right? It comes from the weight of the fluid. I'm going to pick it up from here. Is there anyone who wants to see me after the class?